Welcome you back to another episode of our course for further mathematics SS2. And in this episode, we're going to be dealing with the binomial theorem. Now, the binomial theorem, it is a kind of theorem that has to do with the expansion of numbers based on the Pascal's triangle. Now, Pascal's triangle is basically a triangular arrangement of numbers, and those numbers they have a kind of regularly repetitive pattern, which we will study in this video. Now, what about Pascal's triangle? Let's do the concept. So basically now we have the first question here, and this example we are dealing with the Pascal's triangle. Now the Pascal's triangle is basically a group of numbers that start from the number 1, and those number 1 we basically split it and begin to observe a repetitive and regular property of those numbers. So for example, when we start from 1 on the Pascal's triangle, now if we have an algebraic expression with only one term, we have the term as 1. Then next, let's move to an algebraic expression with 2 terms, 1 and 1. That's 2 terms. So now, if we were to move to an algebraic expression with 3 terms, you would expect it to be 1, 1 and 1, right? No, but that's not the case. Instead, we will have it as 1, 2 and 1. Now, these are the coefficients of algebraic expressions that we actually noticed with the observations of mathematics. So for the single term algebraic expressions with a single coefficient, with a single positive coefficient. So in this case, each of these algebraic expressions, their terms have a single positive coefficient. So for example, we have x. So in this case, we have x plus y. So we have x plus y. Well, we have x plus y raised to power 1. We have x plus y raised to power 2. 0. So and in this case we have if you keep looking at it, basically 1 plus 1 gives the middle term here. So but in this case, let's have 1. Automatically you know that we have 1 on either side. So and then we'll begin to add the internal number. So 1 plus 2, that's 3. 2 plus 1, that's 3. 1 3 3 1, and so on and so forth. So we have in the next one we have 1 4 6 4 1. The next time we have 1 5 5 1 5 10 5 1, and so on and so forth. 1 5 10 10 5 1 rather. So that's gotten by putting 1 in the edges, and then 1 plus 4 5, 4 plus 6 10, 6 plus 4 10, 4 plus 1 5, and then in the other edge we have 1. So I want you to note something. Basically, the numbers at the edges are always going to be 1, and also the numbers in the midpoints are gotten from the sum of the internal numbers, the sum of the numbers before them. So for example, this number is 1 4 6 4 1. We'll put 1 at the edges, and then we'll look at the number before, at the Pascal triangle that was before this one, which is at the first two numbers. We have 1 and 3. We added them, we got 4, and we use that for our new Pascal triangle. Then we'll move to the other one. 3 plus 3 6. We got 6, and move on to the next number, and so on and so forth. So that is how Pascal's triangle is formed. Now, in the binomial theorems, we don't have to rely on Pascal's triangle for the expanding of algebraic expressions. Why? Because we can always make use of the permutation and combination. If you don't understand the concept of permutation and combination, you can check the video before this video in this same course. I've talked about that. So basically, let's begin to solve binomial expansion problems with simple permutation rules, and so that you'll be able to understand it better. So now, we have a question. Find the coefficient of x raised to power 3 in the expansion of 2 minus x raised to power 8. So we have the question as 2 minus x raised to power 8. So we have 2 minus x. And then this 2 minus x is raised to the power of 8. So we're looking for the coefficient of x raised to power cube in the ascending powers. So in this case, we could use 2 ways. We can use Pascal's triangle, and we can make use of binomial theorem. So in the case of binomial theorem, we'll start from the looking at the first term. So the first term will be single on its own, but with a power of 8. So 2 raised to power 8. We'll write it single like that. Then plus. Then moving on to the next term, we will need to look for the combination of this first and the second term in such a way that the first term is reducing and the second is increasing. So we will look at the permutation of 8 with respect to this second term. That will be 8 over. This was 8 over 8 permutation 0, 8 combination 0. That was basically 1. So 8 combination 1, that would be 8 over 1. That's 8 over 1 times 2 raised to power 7 times x times minus x raised to power 1. x raised to power 1. So this is using the combination method. We don't want to just start guessing with Pascal's triangle. Then let's move to the next thing. That's plus 8 over 8 times 7 over 1 times 2. So if you recall, this is another shortcut for looking for the combination of numbers. I did not talk about that in the previous episode of permutations and combination, but you can also grasp that today. So this is a shortcut for also getting permutations, rather for getting combinations. So and then multiplied by. So you notice that the power of this first term is decreasing consistently, but the power of the second is increasing consistently. That's 2 raised to power 6 times minus x raised to power what? Can you guess it? That's 2. So that is it. So but in this case, we've not gotten to where we need, because this here the power of x is still 2. So we need to solve it till we get to the place where the power of x is 3, right? That's then we'll say plus again, plus 2 raised to power 7, 2 raised to power 5 rather. It has decreased from 8 to 7 to 6 to 5. Times 8 times 7 times 3 times 6 all over 1 times 2 times 3 times 2 raised to power 5 rather times 2 raised to power s times minus x raised to power 3. So this is the part where we need. Now the reason why I'm using minus x is because this expansion was by default made for positive terms, but in the case of negative terms, we need to add the negative sign with the term and regard them as 1. So that is why. Now, but if it was plus, we'll make it of only x here. We don't need to put the plus x. Now let's look at this term, because this is where our answer lies. So we're looking for the coefficient of x in this term. So basically, let's evaluate the numerical part. So that will be 2 raised to power 5. That's 2 times 2 4, 4 times 2 8, 8 times 2 6, 8 times 2 32. That's 32 dot 8 times 7 times 6 divided by 1 times 2 times 3. So obviously this 2 times 3 is 6. I mean 6 will cancel 6 here. That's 8 times 7, that is 56 times minus x raised to power 3. That's minus x. That's minus x. That's minus x. That's 32 times 56. Let me try using arithmetic. Let me try using mental arithmetic. That's 6 times 2, 12, without doing much calculations on the board. 6 times 2, 12. Then that's, we'll carry 1. Then we have 3 times 2, 6. 3 times, okay, well, this is quite difficult. So I have to carry 1. 6 times 2, 6 times 3, 18. 18 plus 1, 19. 19 plus 10, that's 29, right? 9 by 2, 2. 5 times 3, 15, 17. That's 1792 x raised to power 3. But in this case, we have minus times minus times minus. That will give us minus. So our coefficient here is minus 1972, 1792. So that is it. You can check it out. That is the correct answer. Minus 1792. That will be the answer of this question. So this is basically the concept of permutation of binary combinations and all these what's called again. This is basically the basics of binary theorem. Was it binary? Binomial, yes, rather binomial theorem. Thanks for watching.